proposed the suggested memorandum for the Physical Sciences Paper 1 for November 2024 for grade 12. Okay, so we have 10 questions that we need to look at. We can use a calculator, instruments, show the formula, and all of that, okay? We're rounding off to 2 decimals. Okay, so with the question 1, which is the multiple choice, we have various options, okay, that we have for answers. And then we can just choose one to be our correct option. Okay, question number 1.1. They're telling us that several forces are acting on a moving object. Okay, so if forces are acting on a moving object, which of the following statements is correct when these forces are in equilibrium? So when forces are in equilibrium, it's more like Newton's first law of motion, that this body is meant to continue in its state of rest or its state of uniform motion. So in this case, it's moving. So the motion must be uniform unless it's acted upon by a net force. So the options we have, the velocity of the object is increasing. No, that is wrong. It cannot be increasing. And the object is moving at a constant velocity. There is some truth in that. The kinetic energy is decreasing. No. The object has a non-zero acceleration. I'll say that is also wrong because the velocity is constant, which means the acceleration must be 0. So option B would be my option for 1.1. Then 1.2, they're telling us that a stone is thrown vertically downwards from the top of the building and takes 2 seconds to strike the ground. If we consider the acceleration time graph below, okay, we're ignoring the effects of friction. What does the shaded area between 0 and t represent on the graph? So what we know, we can use the first equation of motion, where Vf is equal to Vi plus A delta t. Now, when you talk about this area under the graph, so this is the acceleration, and then this side is basically the change in time. Okay, so the area is, okay, the shape is a rectangle, which means the area is just gonna be A delta t. So from this, if we move the Vi that side, which means it's V final minus Vi is equal to A delta t. So this component here is what we call the change in velocity. Let's look at the options. Shaded area between that represents the final velocity, no? The change in the position, nope. The constant velocity of the stone is the change in velocity, which is option D. All right, then 1.3. If a ball that is moving horizontally has a constant momentum, okay, and then the kinetic energy is K, the ball collides with a wall and then bounces back horizontally. So immediately after the collision, the ball has half of the momentum, okay? Then the mass of the ball remains constant. Which of the following will represent the kinetic energy of the ball immediately after? Now, one thing we know about momentum is that it is directly proportional to the velocity, okay? The mass stays the same before and after the collision. So where there is V, I can represent it as a P, okay? Then if I'm looking at the kinetic energy, the EK for the first one is just a K. So which means my EK initially is going to be a half M, I'll say P squared, just in that sort of notion, because P is directly proportional to that. Now, if the momentum is now a half, which means where there is P, I'll represent it with a half P. Everything is squared. So squaring that, I'll get a quarter, then multiplied by a half MP squared, because this is a quarter P squared. take this a quarter away, and then we have our original, which is K. So which means we're going to have a quarter of K. That is option A. Then 1.4, with 1.4, a force F is acting on a box. It moves from rest down a rough incline at a constant acceleration. The force is part of the incline as shown in the diagram below. A force F acts on a box as the box moves from rest down an incline at a constant. So if the box is moving from this point going upwards, we know that the FG parallel will be acting downwards, and then the frictional force will also be acting downwards. That is to the interpretation of the, I don't know, that's what I'm interpreting, okay? If the box moves from rest down a rough incline. Okay, so choose the option that correctly completes the statement. So the work done by the gravitational force is dash dash, the work done by the frictional force, and the work done by F. So if we know that F applied is greater since the object is moving upwards, which means to be a combination of these two, the work done by the gravitational as well as the frictional force. They should be summed up if we look at the F net being equal to MA. Okay, so we're going to say the work done by the but now the question is focusing more on the gravitational force, which means work done on the gravitational force must be the difference. Okay, so that is force applied is equal to the work done by the frictional force plus the work done by the FG parallel. So work done by the gravitational should be the difference between force applied and that. Okay, but if it is the difference, is it going to be greater or it's going to be less? It's going to be definitely less, but let's go with option D. That is focusing on the difference between the work done by the friction and the work done by F. So I'll go with option D. That is according to me. We can have various opinions about that. 1.5. If a ball is falling vertically downwards from point A, strikes the ground with a velocity v, okay, and bounces off, reaching a maximum height b, as shown in the diagram below. Which one of the following combinations is correct for the direction of the impulse of the ball upon striking, and then the magnitude of the velocity with which the ball leaves the ground? Okay, one thing we need to know is that since this ball is striking the ground, okay, the direction of the impulse needs to be upwards. Because remember I said impulse is the same as the change in momentum. Okay. So if it is upwards, then we're looking at option A and option C. But then the velocity with which the ball leaves the ground. Now, since the ball is going to be in contact with the ground, there has to be loss of energy. Okay. And if energy is lost, remember the collision is not perfectly, or it's not perfect. So which means there's going to be loss, which is inelastic collision. So which means the velocity must be less. So I'll go with option C. 1.6, they're telling us the absorption spectrum of an element surrounding a moving star is observed on Earth and found to be red shifted. Which one of the following combinations is correct for the movement of the standard frequency of the observed light on Earth? Now, for as long as the spectrum that is observed is redshifted, what must come into our minds is that that star should be moving away. So we have option A and option C. Now, if the star is moving away, It simply means that the wavelength is increasing. Okay, so as the wavelength increases, the frequency must decrease. So I'm going to go with option A that talks about moving away, but then the frequency decreases because the question is focusing on the frequency. So option A will be my best option for 1.6. I would have gone with that. Then 1.7, if we have two small identical spheres, each with a mass of M and charges plus Q are placed in a vertical cylinder, the spheres remain stationary when their centers are apart, as shown in the diagram below. Ignore the friction effects. Which of the following will be an expression for correctly calculating the distance r? So from Coulomb's law, we know that K Q1, Q2 over R squared. Let's cross multiply, which means that is KQ, since Q1 is the same as Q2, that's going to be Q squared over F. Then you take the square roots. It means it's the square root of KQ squared over F. Okay. So before we even look at the simplified versions, let's look at the options we have. The only option that has a KQ squared is option A. We know that force can be mass and the gravity, which is more like the weight or something. The rest, the KQ squared, is at the bottom, which doesn't make sense in option D. So my best option in this case is going to be option A. 1.8 kilowatt hour. This is a unit of, is it power? Power we know is just the rate at which work is done. Okay. And the unit for power is just watt. Electric current, we use amps. Potential difference, we use volts. Okay. And then electrical energy, that's where we use the kilowatt hour. So option C would be the best for 1.8. Then 1.9, the diagram below shows a simplified electric motor. Okay. So the rotation of the coil is observed from the battery. So what we need to know is, what is the question asking for? Which one of the following statements is correct while the motor is in operation? So we need to get the direction of the coil. We have anti-clockwise and clockwise. Okay. So if this is the positive terminal and this is the negative, we know that electricity will flow in that sort of direction. Now with the motor, we normally use the left-hand rule. Okay. So if this is our B, in that case, the current is acting in that direction. So B is a current, which means the force is going to act downwards. Okay, that is the current, and then that is the B. So the force is acting downwards. So if it's acting downwards, which means it's an anti-clockwise. Okay, so if it is anti-clockwise, the question is, which means we're looking at A and D. Okay, so if it's anti-clockwise, is it the slip rings that are going to rotate, or it is the commutator that's going to rotate? Now, since it's a motor, I'll go with option D, because it's the commutator that must rotate. The commutator is connected to the coil. So option D will be the best. Then 1.10, which of the following statements is all true for the photoelectric effect? True is in capital letters. Okay, chances are high all these statements are true about light. Okay, so number one, they're telling us light has a wave nature, which is very correct. That is, if you're talking about reflection, diffraction, and so on and so forth. Light has a particle nature, which is also correct. And then light energy is quantized, which is also correct. Now, which option do we have? Remember, we don't have an option that has three of them. So we need to get the option that usually focuses on just photoelectric effect. And in that case, we shall have option 2 and then option 3, because option 1 does not demonstrate whatever photoelectric effect. So option 2 and 3 is going to be a D. Okay, so that is 1.10. And that's the end of question 1. Okay. Then question 2. In an experiment, we have a crate of mass 8.5 kilograms that is lying stationary. Okay, that's the keyword. On a rough horizontal table, it's connected to a mass hanger by means of a string that is passing over a pulley shown. Mass pieces will be added bit by bit up until the crate starts to move. The experiment will be repeated with different masses. We're ignoring air friction. So we have this, and then we have this graph, which means we're going to have to use both of them simultaneously or concurrently. All right, then 2.1. They want us to define what static friction is. So we know that the type of friction that exists between the object and the surface just before motion takes place. Okay, so we're saying the type of friction that exists between the surface and the object. Okay, so we know that this type of friction does not allow motion to take place. It keeps on holding the object in one place. So a definition of that sort would guarantee you those two masses. Then 2.2, they want us to draw a labeled free body diagram showing all the horizontal forces, only horizontal forces that are acting on the crate before it starts moving. And so what we have is that there's going to be that tension in that case, and then there's going to be the static friction in that direction. So the tension and the static friction are going to be equal to each other. That's why there's going to be no motion initially. So all we have to do is, this is tension. Let's call it tension, which is T. And then in this direction, we shall have our Fs. I'll not call it Fk. It's Fs, which is the kinetic. So it's the static friction force. All right, then 2.3.1, they want us to calculate now the coefficient of static friction, which is the mu s. It's for formats. And so my approach to this would be to look at the entire system. Or I can start by looking at each body independently, okay? But one thing I know from this graph is that at this point where the body is experiencing static friction, the amount of weight that was put there was just 4.2 kilograms. Okay. So what I'll do, I know that my Fs is going to be the mu s multiplied by the normal reaction. But I don't know the Fs. I can get the normal force. So for us to get the Fs, which is here, we can say that Fnet is equal to Ma. So if I look at the weight that is acting downwards, so it's going to be the weight minus the Fs should give us the mass and the acceleration. But we know that the system is not moving, so which means our acceleration is going to be 0. So the weight should be equal to the static friction force, which weight is 4.2 multiplied by 9.8. So when I punch that into the calculator, 4.2 times 9.8, I end up with 41.16. Okay, 41.16 newtons. Now this is going to be our Fs. Now we're going to get this and replace it outside. So we're saying Fs is mu s multiplied by the normal reaction. which means the coefficient that we need is 41,16 divided by the normal force, which is more like the mass, and then the acceleration due to gravity. So I'll say it's 8,5 multiplied by 9,8. So I'm not including the 4,2 because this static friction is just between the crate and then the surface. So when I divide that, that is 8,5 times 9,8. That gives me 0,49. Now remember, this is a ratio, so we don't expect units to be added. So that is the coefficient of static friction. Okay, then 2.3.2, they want us to get the magnitude of the acceleration represented by y. On the graph, if the coefficient of kinetic friction between the crate and the table is 0,4. So I'll say that my mu k is 0,4. But we know if this is going to be 8,5 kilograms, we know that the weight that creates the acceleration is going to be 7,4 overall, which means the 4,2, they kept on adding up until they got to the 7,4 before the motion would start. So I'll have a 7,4 down here, that's kilograms. Then I can just do the application of, so the weight will be downwards, the kinetic friction, we can get to that side. They want us to get the acceleration. So let me start by getting the Fk, which is the mu k multiplied by the normal force. In this case, it's just gonna be the 0,4 multiplied by the 8,5 multiplied by the 9,8. So punching that into my calculator, what do I get? 0,4 times 8,5 times 9,8. That gives me a 33,32 newtons. That is the kinetic friction force. Then using the F net is equal to MA. So I'm going to have the weight minus Fk must give us the mass as well as the acceleration. Now this mass is just going to be the combined mass of the two since there's acceleration. Okay. So the weight, which is leading, is the 7,4 multiplied by 9,8. Frictional force, we said, is 33,32. Should be equal to, we know that 8,5 and then 7,4 gives us 15,9A. When we subtract that, okay, we have 7,4 times 9,8. I'm getting 39,2 here. Is equal to 15,9A. Then divide both sides by 15,9. Okay, that cancels that. So our acceleration becomes 2,06, which I'll just round off to 2,47 meters per second squared. Okay, so that is how I would have approached that question. And then 2.4 are telling us that a 5-kilogram block is now placed inside the crate, and then the experiment will be repeated. How will this affect the maximum static frictional force now experienced by the crate? We need to choose increase, decrease, or remains the same. Now we say if now there's a 5 kg that is added, which means we're going to have 8,5 plus 5, which is now 13,5. So if that happens, which means you need quite a lot of force to move it. In other words, the static friction force is going to increase. It's going to be harder to move that block. Okay, so what will happen? How will this affect the maximum? So it's going to increase. What you can tell us is the static friction force is directly proportional to the normal force. Okay, so we're saying direct proportional. to the normal force, which is directly proportional to the mass. That would be the explanation. Tell us static friction is directly proportional to the normal force. So by you increasing the weight, you're indirectly increasing the normal force, which in turn affects the friction force. Okay, so that is question number 2. Question number 3. Question number 3. Telling us that there's a ball A that is thrown vertically upwards at 12 meters per second from the top of a building. 2 seconds after A was thrown upwards, ball B is thrown vertically downwards at 5.4 meters per second from the top of the same building. Both balls A and B strike the ground at the same time, T seconds. We have the position time graph. There we go. So let's summarize this and say that if we have ball A, the initial velocity is going to be 12 meters per second. Then if we look at ball B, is this all we have? Yeah, let's look at ball B. Ball B, the initial velocity is going to be 5.4 meters per second. Now remember the directions are different. One is up and then the other one is down. So since ball B is striking or is being projected downwards after 2 seconds, which means it's time. In this case, for A, the time will remain as a t. We shall take its time to be t, and then this one, we shall take it to be a t minus 2. Okay, I'll use the time to be t minus 2. Now, for us to answer the question, because they want us to use just equations of motion only to calculate the value of each of the following. They want us to get the t, the time when the 2 blocks strike the ground. So for that to happen, the 2 blocks would have traveled more or less the same distance. In other words, displacement of the 2 bodies will exactly be the same. So delta y of A must be the same as delta y of B. Okay, so what we're going to do in this case, I'm going to look at body A, first of all. Okay. Or I'll call it ball A. So my delta y of A from delta y is equal to V initial delta t plus a half A delta t squared. Let's start with the formula. Then let's do the substitution. So initially it was a 12. Okay, it's just a 12, there's no comma. Okay. Then we're multiplying by t. And then since the object is moving upwards, I'll say minus. I'll take the g to be minus. That's a half into negative 9.8 with a t squared. Simplify this. It's gonna be 12t minus 4.9, but t squared. This is change in YA. Then I look at ball B. Ball B, how many marks is this question? It's 5 marks. Yeah? Okay. With ball B, I'll repeat the same thing. So change in Y is gonna be V initial multiplied by T plus a half A delta T squared. Do the substitution. So that's gonna be initially, it was projected downwards. So I'm gonna say negative 5.4 into the time for B, we said it's T minus 2. Okay, plus now it's gonna be a half. Why am I putting a bracket here? Okay, that's gonna be 9.8 into T minus 2 squared. Okay, then when I open this up, I'll have negative 5.40 plus a 10.8 minus 4.9 into T squared minus 40 plus a 4. Okay, so we say, okay, let me just simplify this before I can equate the 2. So negative 5.40 10,8 minus 4,9 t squared plus that's gonna be 36, 19,6 t minus 19,6. Simplifying this further, it's gonna be negative 4,9 t squared, this and that. So 19,6. We are subtracting 5,4. That's going to give me 14,2. And then the 10,8, I subtract the 19,6. That gives me negative 8,8. So this, I'm equating it to the first one, which was a 12t minus 4,9 t squared. All right, so we're seeing that this is going to cancel that. Both of them are negatives. And then, so I have to move, which one? Let me move the 14 to that side. So negative 8,8 is equal to 12 minus that, which gives me, let me see, I have 12 minus 14.2, which is negative 2,2t. Then I'll divide both sides by negative 2,2. Okay, so which means my t is just 4 seconds. So after 4 seconds, that's when the two balls will strike the ground. Then they want us to get Z, which is the height of the building. Okay, the height of the point of projection. So for me to get that, I can still use what I was using initially to say that delta, this is 3.1.2. Delta, no, it's not delta, it's just a YA is equal to V initial delta T plus a half A delta T squared. Okay, so we're looking for the height. Initially, it is a 12. The time is taking 4 seconds. Plus a half times negative 9,8 multiplied by 4 squared. Okay, so that's a 48. When I look at that side, I'm having 0,5 times 9,8 times that, which gives me negative 78,2. So when I subtract that, I'm going to end up with a 30,2 meters. Now, since the displacement is below the point of projection, that's why we're having the negative sign. So which means the height of the building, or you can just tell us that Z is 30,2 meters. It's 30,2 meters. All right, then 3.1.3. 3.1.3. They want us to get Y. Y is just the maximum height reached by ball A, okay, from the ground. So I can get the maximum height from the point of projection, and then the answer I get, I'll have to plus what I obtained in 3.1.2. So we note that I can use the VF squared is equal to V initial squared plus 2A delta Y, okay, of say A. So we know that at the maximum height, the V final will be a 0. So 0 is equal to 12 squared plus 2 times negative 9,8, and then delta, you can say delta Y. Okay, so that's going to be 144 minus 19,6 YA is 0. Move the 19,6 that side. Okay, is equal to 144. And that's a negative. Divide both sides by negative 19,6. Okay, which means YA. So 144 divided by 19,6. That gives me 7,35 meters. So that's just the height from the point of projection. Okay. Now, since I'm looking for the height from the ground, I have to plus the 30,2. So this gives me 37,55. Is that so? 7,35 plus 30.2, which is 37,55 meters. So this is the Y value. Okay, so that would be my approach. Just let me know in the comment section how you approached this question. Then in 3.2, they want us on the same set of axes to sketch the velocity time graphs for A and B. Or while they are in free fall, we need to label graphs A and B for both balls. Clearly indicate the following on the graphs: the initial velocity for each ball, the time, that is the time at which each ball is thrown, and then the time at which they strike the ground. So we know that velocity time graphs are usually straight lines. Né? So this side we shall say velocity in meters per second. This is the time in seconds. Now, do we need to do further calculations as in the time with which? I doubt whether that will be necessary. So we know that it takes 4 seconds, né? If that is 4. And then halfway, that's when the second ball is projected, because they told us 2 seconds later. All right, so initially for ball A, the initial velocity was 12. So if that is our 12, I know that it will hit it will reach the maximum height around about this point, just before the other ball is projected. Okay, so which means before the 2 second mark. Can have it somewhere in that direction. And then it moves up until the 4 seconds. I don't know what velocity it will be here. Okay, so I'm gonna call this ball A, or you can just label it as A, graph A. Then graph B, it's having 5,4 in the negative direction. So I'm gonna have a 5,4 somewhere there. Okay, but then this 5,4 is going with, it's going to be projected from 2 seconds. So this time, then the graph will just move up until the 2 meet up. Okay, or it's not a big deal for them to meet up because they're not telling us that they are hitting the ground with the same velocity. It's just the time that is basically the same, okay? So even this, it can slightly be different, whereby we just have it in that sort of direction. Okay, it can be more or it can be less, depending. So this is ball B. So that would be my approach to that. Remember, the ball was not just dropped. Had it been that it was dropped, then it was going to start from here. Okay, so that is how I would have approached that 3.2. All right, question number 4. They're telling us that 2 trolleys, trolley A and B of masses 1,5 and 2 kgs respectively, are held stationary on a straight horizontal frictionless track. So if the bodies are held stationary, which means the velocity there is a 0. Okay. If the trolleys are released and the spring takes t seconds to return to its original length, the spring then falls to the ground. So as soon as it is released, it will give these 2 bodies some bit of momentum. Okay, so that they can move. They told us this one to the right and then that one to the left. Trolley A moves to the left while B moves to the right and then up a frictionless inclined plane, rising to a maximum height of 1,5 meters, as shown in the diagram. Okay. And then 4.1, write down the principle of conservation of mechanical energy in words. So we know that in an isolated system, the total mechanical energy is conserved. Or in an isolated system, the total mechanical energy remains constant. Then 4.2, calculate the speed of trolley B at the bottom of the incline. Now, what happens that when the first question asks about conservation of mechanical energy, which means the question that follows should be more like the application of the mechanical energy. So we know that at this bottom, at the bottom of the incline, we're gonna have the EK max. And then since they told us that this object, is it gonna stop? Just moves to the right and then up a frictionless rising to a maximum height. So this is the highest point. So in this case, if the highest, which means we're gonna have EP max at that point, okay? So kinetic energy and then the potential gravitational energy. So I'm just gonna compare the two and then I'll get my velocity before the incline. So I'll say EK max should be equivalent to EP max. So this is gonna be a half mv squared is equivalent to mg multiplied by height. Do we know the mass of the body? It's not a big deal. I can even cancel that out. I mean, it's the same body. No? Then since we're looking for V, I'll say V squared is going to be 2gh, and then I can find the square root, which is 2gh. So 2 times 9,8 multiplied by the height, which is 1,5 under the square root. Okay. So if I punch this into my calculator, multiplied by 1,5, this becomes 5,42 meters per second. So that is the velocity of this trolley B just before the incline. Okay. Then 4.3. For the t seconds that the spring takes to return to its original length, can we calculate the change in momentum of trolley B? So we know that trolley B, can we go back to the question and see? They're telling us that trolley A moves to the left, that moves to the right. Okay, where is that thing that's, okay, the trolleys are released and then the spring takes t seconds to return to each natural length and the spring falls to the ground. So as it's falling to the ground, the trolleys move left and right. Okay, so what's going to happen here is I'm going to look at the velocity that I calculated, which is the 5,42, and then the initial velocity, which was a 0, okay? So I'll say that the change in momentum of body B is going to be the mass of B multiplied by the change in velocity. So the mass of B is 2. Yes, that's correct. So that is 2 multiplied by the 5,42 minus the initial velocity, which was 0. So that's just going to be like 2 multiplied by 5,42. That gives me 10,84. That is kilogram meters per second. So that is 4.3.1. And then 4.3.2, they're asking us for the change in momentum of trolley A. So with trolley A, since we've looked at momentum being conserved, it's just going to be the same change in momentum. Okay, it's going to be the same change in momentum, but just in the opposite direction. So if this one was to the right, then this should be to the left, just in the opposite direction. Then 4.4, they want us to calculate the speed of A after the t seconds. So we know that the change in momentum of A is also going to be the mass of A multiplied by the change in velocity of A. So we know that the change in velocity, let's substitute. We say this is 10,84 is equal to the mass, which was 1,5, into the velocity V final minus the initial. Okay. So we're just going to have 1,5 V final of A is equal to 10,84. Let's divide both sides by 1,5. All right, so 10,84 divided by 1,5, this becomes 7,23 meters per second. So a smaller body will have more velocity than a bigger body, which is kind of logical, okay? All right, question number 5, a constant force F is applied at an angle of 30 degrees to the horizontal of a crate, which is having 6 kilograms. That was initially at rest, as shown in the diagram. Constant frictional force of 10 newtons acts on the crate as it moves from A up until B along a horizontal surface. The distance between A and B is 1,5. The speed of the crate is 2 meters per second. All right, so we have the frictional force, which is 10 newtons. We have the velocity, which is 2 meters per second. And then the distance, I'll say delta x, is 1,5 meters. All right, they want us to define the term work done by a force. So we know that work done by a force is basically the product of the force applied on an object and the displacement of the object in the direction of the force. So the product of the force applied and the displacement, which should be in the direction of the force. All right, so that is 5.1. Then 5.2, they want us to draw a labeled free body diagram showing all the forces that are acting on the crate as it moves. It's for 4 marks, which means we should expect a minimum of just 4 forces, okay? So we know that we're going to have the force applied at that angle. We're going to have the weight. Some people call it FG, no problem. And then we're going to have the frictional force because they told us it is there. So we're going to call that FK. And then we're going to have the Fn, which is the normal force. So 1, 2, 3, 4. Perfect. All right, then 5.3, they want us to use energy principles only to calculate the magnitude of F. So what we can see, or what we know with energy principles, is that the net work done, W net, is equal to the change in kinetic energy, okay? So when I look at the work done or the net work done, it's going to be the work done by the horizontal component of the F, since the object is moving horizontally, which is going to be the F cos of 30, okay? And then I have to subtract the work done by the frictional force. And then in that way, I should be able to get what they're asking for. Okay, so I'll start by looking for W net, which is going to be the work done by F plus the work done by the Fk. So work done, we said it's F delta X and then the cos of theta. So work done by the F is going to be the F cos of 30. The displacement is 1,5 multiplied by the cos of 0. Plus, they gave us the frictional force, which was a 10, which is to our advantage. So 10 multiplied by 1,5 and then the cos of 180. Okay, so when I simplify this, do I need to, well, let me just equate it once to the change in kinetic energy, which is a half. The mass, okay, the mass is 6. Okay, and then the final velocity. Do we know the final velocity? Yeah, they told us the speed of the crate at B is 2. So which means it's going to be times 2 squared minus a half times 6. Initial velocity is 0 squared. All right, then I'll have this simplified. So 15 cos of 0 is going to give me the same 15. Then when I multiply it by the cos of 30, that should give me the, where am I having something big? Is it 15? No, it's 1,5, sorry. 1,5 cos of 30, which is going to give me 1,299. Okay. This is going to give me a negative 15. Okay, because of the cos of 180, there is F here. Let me just write this out nicely. Okay, so we're saying it's 1,299F minus 15 is equal to a half. That's 4, which gives me a 12 minus 0. Okay, so 1,299F, when I move the 15 that side, I'll get a 27. I'll divide by 1,299, 1,299. That cancels that. So 27 divided by the answer gives me 20,78. Oh, let me just leave it as 78. 20,78 newtons. So that is my applied force. All right. Then 5.4, they're telling us that now a 2 kg object is placed inside the crate. What's happening in this paper? Like every question, we are adding weight. Okay, so we have another 2 kg that is added here. So which means this is going to become greater. Okay, what effect will this have on the work done by the same force if the crate has to move from point A to B? So the explanation is, for as long as the force is the same, okay, without the condition of A to B, the distance that will be moved would be smaller. But then for us to satisfy the distance of 1,5, a lot of work needs to be done to overcome the frictional force. Remember, we said frictional force is directly proportional to the normal force. Frictional force is directly proportional to the normal force. So with 5.4, we're just going to say increase. Okay, 5.4, I'm going to say increases. The work done must increase. All right, question number 6. Question 6, a stationary listener. Okay, stationary listener. So the velocity of the listener is 0. Standing on the roadside records the wavelength of the sound emitted by a siren of a police car that is traveling at a constant velocity. 0 acceleration. Okay, let me call this velocity of the source. In the wavelength time graph below, which is not definitely drawn to scale, delta, no, this is lambda. Lambda L is the wavelength of the sound recorded by the listener, and then lambda S is the wavelength of the sound emitted by the siren. Okay, the speed of sound is 343, perfect. Now we can see that the wavelength that is recorded is higher than the wavelength that the source is emitting. All right, 6.1. Name the phenomenon that explains why the wavelength shown in the graph will differ. So that phenomenon is what we call Doppler effect. Okay, then this question 6.2 is the car moving towards or away from the listener? We must give a reason for the answer. Now, if the listener is getting a higher wavelength compared to this, let's go back to the, what do you call it? To the formula of speed and whatever. So we know that V is equal to F lambda, okay? Which means that frequency is inversely proportional to the wavelength, okay? So if the wavelength is smaller, okay, so if the lambda is small, then we know that the frequency is going to be high. And then if the lambda is big, then we know that the frequency is going to be small. So in this case, since the wavelength here is big, which means the frequency that the listener gets is low. It's a lower frequency. And then since the wavelength is small there, then the frequency here is going to be high. So the frequency of the source is high, and then the frequency of the listener is low. So the frequency that the observer records is smaller than what is actually emitted. And that scenario happens or occurs when the object is moving away. So I would take away to be the option. Okay, just let me know what you did there. Then 6.3, calculate the frequency of the sound that is emitted by the siren. So I can still use this formula, okay, and do the substitutions. So we know that frequency of the source is going to be C, which is the speed of sound in air, divided by the wavelength. So 343 divided by the wavelength of the source, which is 0.38. So 343 over 0.38, that becomes 902.63. 902.63 hertz. All right, so that is 6.3.1. And then 6.3.2, they want us to get the magnitude of the velocity of the car. Now, since we have the velocity of the source, we can also get the frequency of the source. We can get the frequency of the listener as well using the same sort of approach. Okay, so 343 divided by 0.4. All right, 343 divided by 0.4, that is going to give me 857.5. This is hertz. So I have the frequency of the listener, I have the frequency of the source. Now, from the formula of Doppler, we know that V, since it's moving away, it's going to be minus over V plus Vs multiplied by Fs. I hope that is the rightful formula, okay? Then we're looking for velocity of the source, this one. Okay, so let me do the substitution. So the listener is having 857.5. This is 902.63, okay? Is equal to velocity of that is the speed of wind, which speed of sound in air, okay? 343 minus the listener who was just standing, velocity of the listener. This is 343 plus the velocity of the source, okay? So on the left-hand side, if I'm to divide that, 857.5 divided by the 902.63, that gives me 0.95 is equal to 343 over 343 plus Vs. When I do the cross multiplication, I'm getting 325.85. This is 343. Okay, so 325.85 plus 0.95 Vs should give me 343. I need to move this that side, so 0.95 Vs. That's gonna be 325.85. Okay, this gives me 17.15. Then I'll divide both sides by 0.95, which means the velocity of the source, I'm getting round about 18.05, I don't know, meters per second. Guys, please let us know how you approach this and what you got. That's 18.05. All right, then question number 7, which is, all right, question number 7, they're telling us that electrostatics, P is a positive 2 nanocoulomb point charge. X is a point that is 6 meters away from point P, as shown in the diagram. All right. So in this case, they don't want us to define they can't be that stingy. In our definitions, we're just gonna be 3 marks. All right, they want us to get the magnitude of the electric field. So we know that the formula for electric field is KQ over R squared, okay? Whereby our K is 9 times 10 to the 9. We are multiplying by 2 times 10 to the negative 9, the nano is at times 10 to the negative 9. Over the distance of separation, we can change this to meters, which is going to be 0.06 squared, because it's 6 divided by 100. Hey, let me confirm, guys. It is 0.06 squared. All right, perfect. Then we just punch this into the calculator. That's going to be 9 times 2 divided by 0.06 squared. I'm getting 5,000, like 5,000 Newton per Coulomb. Okay, so that's what I'm getting. Or alternatively, you can just say 5 times 10 to the 3 Newton per Coulomb. There's no problem with that. All right, then they're telling us that now there is point charge S with a charge of negative 2 nanocoulomb that is placed 4 centimeters to the right of P. Okay. Remember, this was X. Okay, let me just put X here. And then this is going to be 2 centimeters to make it 6. Okay. Then they want us to draw the resultant electric field pattern due to P and S. So we know that P is a positive, S is a negative. So if we have opposite charges, what happens? There's going to be attraction, okay, whereby the field lines must be moving from the positive to the negative, okay? One other thing we need to know is that the number of field lines that are leaving E should be exactly the same number of field lines that are reaching Q. So I call this, is it Q or S? It's S, that are reaching S. Okay, so I have this, have that, this and that. So it's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Perfect. So it should be entering. So it doesn't matter how many lines are going there, for as long as there's some bit of attraction and field lines moving from one point to the other. All right, guys. So that is how 7.2 would have been drawn. Then 7.3, they're telling us that now there's a third point charge T that is placed 2 centimeters to the right of S. Now remember, this was point X. Remember that side from the original point. So it's the same as the X point. Now we are replacing X with just a charge T. 2 centimeters to the right of S as shown in the diagram, then point charge T will experience a net electrostatic force of this much to the left, which means this force is kind of negative, the net, based on the direction. Then 7.3.1, they want us to state Coulomb's law in words. So we know that with Coulomb's law, the force of attraction or repulsion that exists between 2 point charges is directly proportional from the formula. This is Q1, Q2 over R squared. So the force of attraction or repulsion between 2 point charges is directly proportional to the magnitude of the product of the magnitude of the charges and inversely proportional to the square of the distance between those charges, or the square of the distance apart. Then 7.3.2, what is the polarity of charge T? Is it positive or negative? All right. So what we need to understand with this is if, let's say, we call this, okay, if our resultant as a result of everything is negative, chances are high this is going to be a positive. Okay, let's see. Initially, for the point charge, we had the 5,000 somehow, no? Which was positive, but that was just a point charge. So let's say I make this a negative. We know that this positive and the negative is going to cause attraction. Okay, which means the force that is acting on T is going to be to the right. Then if we're looking at S and T, it's going to be a repulsion, which means to be pushing this away and also pushing, which means our net should be to the right if the charge is negative. So which means the charge cannot be negative. If it's positive, we know that a positive and a positive will cause some bit of repulsion, okay, which is fine. But then this negative and a positive will cause some bit of attraction so that the overall net force, remember, the smaller the distance at the bottom, the bigger the force, okay? So the force between S and T must be greater than the force between P and T. All right, so we're going with positive. Okay, then 7.3.3, I want to strike the magnitude of charge T. So what I did, I looked for the force between P and T, which is KQ of P, Q of T over R squared. So 9 times 10 to the 9 multiplied by 2 times 10 to the negative 9 multiplied by QT over 0.06 squared. Okay, so the force of P and T is, remember we simplified this earlier on, which is just 5,000 QT. Then let me look for the force between S and T using the same approach. So 9 times 10 to the 9 multiplied by 2 times 10 to the 9, and then QT divided by 0.02 squared. Okay. So punching that, I will have just 18, okay, over 0.02 squared, which gives me 45,000. This is QT. Okay, so initially we said this is a plus, this is a negative. So this is going to be positive, this is going to be negative. Then if we include the net into our calculations, which is the 2.5, so I have the 5,000 QT, and then I also have the 45,000 QT. Combining these two, we must get the 2.5, okay? So F net, so it's 2.5 times 10 to the negative 4 newtons. Okay, so what I'm going to do there is if I get my 5,000 minus my 45,000, it must give me the 2.5 times 10 to the negative 4. Okay, subtracting this, I'll get negative 40,000 QT is equal to 2.5. Remember, this was a negative, so even if we leave it as a negative, since it was acting to the left. So divide both sides by 40,000 and then over 40,000. So QT, that's 2.5 times 10 to the negative 4 and dividing it by 40,000. All right, so I'm getting 6.25 times 10 the negative 9. Yeah, times 10 to negative 9. Or you can just write it as 6.25 nanocoulomb. All right, so that is my approach to that question 7. Question 8. Question number 8. They're telling us that L1 and L2 are two light bulbs that have the following ratings, okay? L1 is rated 36 watts, with 20 volts, while L2 is rated 48 watts and then 32 volts. The two bulbs are connected in the circuit diagram below, and then the battery has an internal resistance of 0.6, while the conducting wires and ammeters have negligible resistance. It's only the ammeters and the wires whose resistance we can consider. R1 and R2 are resistors, just as the question states or indicates. And then they are asking us, okay, so we can see the lights are there and all of that. Then they want us to define the term power. Okay, so we know that power is basically the rate at which work is done or the rate at which energy is transferred. Now, for the sake of electricity, we shall look at the rate of energy transfer. Okay, so that is the definition of power. Then 8.2, they want us to get the reading of A2. Where is A2? A2 is here. Now, we know that this bulb is in parallel with this other section. Now, before we even start answering that 8.2.1, we need to know that bulbs, since they have ratings of how much power and how much voltage must go through them, it simply means they are also resistors, okay? So I'm going to consider those bulbs to be resistors as well. So meaning that for me to get the current that is passing through there, I can look for, we have L2, what is the rating of L2? It's 48 watts and then 32 volts. So 48 is the power, okay? And then the voltage or the potential difference is 32 volts. So the formula of power that combines current and voltage is that P is equal to VI. I think that is perfect. Yeah? P is equal to IV or VI. Then for me to get the current that the question is asking for, I'll get my power divided by the voltage. So the power is 48. The voltage is 32. Okay, so use your calculator. So 48 over 32, this gives me 1.5 amps. Okay, so there's a 1.5 within the L2. All right, then 8.2.2, they want us to get the ammeter reading A1. So looking at the connection of A1, this ammeter is reading the total current within the circuit, okay? So if I can find the current that is passing through this bulb, we know that the current between this bulb and then this R1 is just going to be the same current. And then I'll plus the two values to get my total current. So I'll say the current through 1, because this was current 2. So current through 1, we can use the same thing, power over V, which is now, is it a 36 over 20? Okay, 36 over 20, that's going to give me 1.8 if I'm not mistaken. Okay, that is 1.8 amps. Then the reading, total current, will be I1 plus I2, because the total current is split up into I1 and I2. That's going to be 1.5 plus 1.8. 1.5 plus 1.8 gives me 3.3 amps. So that is what I would have done for 8.2.2. Then for 8.2.3, they want us to get the resistance of R1. The resistance of R1. Now, what I know, or what I should know, is that this one was 48 watts and then 32 V. This was 36 watts and then 20 V. Now with a parallel combination, this and this one are in parallel, okay? So for as long as they're in parallel, the voltage across these two has to be the same. But R1 and this bulb are in series. And if they're in series, there is a voltage breaker. Okay, the voltage is different. The voltage here will be different from the voltage across the R1. Now, since L2 is the only resistor up here, and we know that the total voltage across is 32, which means even the total voltage across this one must be at 32. So I'll start by getting the voltage across R1, which is going to be 32 minus 20, because I know that this is the biggest value, which is the 32. If I subtract the 20 or if I add whatever I have to add, I must get the 32. So that's going to give me 12V. So across R1, we have 12 volts, okay? But we say that the current that is passing here is 1,8. So we can use 12 and 1,8 and get the value of R1. So I'll say that from Ohm's law, where V is equal to IR, we're looking for R, which is the voltage over the current. So our voltage is 12. Our current is 1,8. So 12 divided by 1,8 gives me 6,67 ohms. Alternatively, you can give it as a fraction, just as a 20 over 3 ohms. So that is what I'm getting for that resistor. Then 8.2.3 is done. Yes, that is done. Then 8.2.4, they want us to get the EMF of the battery. So EMF, we know that the formula for EMF is I into R plus small r. We know the current. Oh, how about if I look at it in a different way, whereby I use the voltages? Okay, saying EMF is I into R plus small r, or EMF is V external plus the V internal. Okay, because for the V internal, I'll just get my current multiplied by that. My V external, I'll get the voltage. Is it the voltage? I have to still calculate. Let me see the voltage across. Okay, because now these two, if I get the voltage across the 4 ohm, and then I add it to the 32, is it going to give me the same answer? Let's see. Let's see. So the voltage across the 4 ohm resistor, okay? We know that the current is going to be 3.3. And then the resistance is 4. So voltage is IR, which is 3.3 multiplied by 4. 3.3 times 4, that gives me 13.2 volts. But remember, we said the total voltage across the parallel was 32. Then total external voltage. Total external voltage is going to be 32 plus 13.2. 32 and 13.2, I'm getting 45.2 volts. Okay. Then, which means that my EMF is going to be the external, which is 45.2, plus my V internal is the current, which is 3.3, multiplied by the current, which is 0.6. So this plus, we're saying 3.3 times 0.6, I end up with 47.18 volts. Guys, I don't know, but that's what I'm getting. That is what I'm getting. You could have obtained something different. Feel free to share with us how you approached your question in this case, okay? Then 8.3 for 5 marks. Hey. L1 burns out. Push, kaput, this one goes. It's normal. Assume that the resistance of L2 is still the same. Okay, it is still the same. While L2, or will L2 continue to glow after L1 burns out? Choose a yes or a no. And then we must support our answer with a suitable calculation. Okay, before we get to the calculation part, let's just understand what happens when there's a burnout, especially with a parallel. So if this burns out, which means there's no more current that is passing through this route. So all the current, all the 3.3 amps will be channeled through this route, okay? Meaning that the 4 ohm and the bulb are going to be in series. And if that is the case, okay, and if that is the case, we need to find out whether this bulb, okay, is going to be able to handle the power that is going to be generated as a result of that single route. So before I say yes or no, let me start by calculating the new power, because I know that the voltage definitely is going to stay the same as a 32. So voltage is going to be 32. Now the current is 3,3. Let's get the power. And then from the power, let's try to compare it with the power rating that we have. Okay, so I'm going to say that power is going to be IV. So the current is 3 times 3, because remember it is in series, which means the current stays the same across the bulb and even across the 4 ohm. Okay, so multiplied by the voltage, which is 32. Okay, so 3.3 times 32, 3.3 times 32, that gives me 10, not 10, it's 105.6 watts. Okay, so this is the power that now will be generated within that bulb. Yet the rating of the bulb is 48 watts. Will the bulb continue to glow? To be honestly, the answer is going to be a no. The answer is going to be a no. Reason is saying that the rating is smaller than the power that will be generated. That will be generated. So we don't need all these whatever paragraphs of explain. So it's a no. We can have our calculations here. Okay, power, we have 105 and that. So normally when these bulbs are made, they have specific ratings, okay? So if, let's say we force the 105, the filament is going to heat up so much that it will end up melting or burning out. And in that case, there will be no light. Okay, so that is how I would have approached 8.3. So overheating will cause the failure of the bulb in that case. All right, so that is question number 8, which is our dear electricity. Then question number 9. The graph below shows how induced current in a generator varies with time. So what type of generator is this? We must choose AC or DC. Now, based, okay, so based on the graph. So based on the graph, I'm gonna go with the DC, okay, because with the DC, we just have those humps. Had it been that we had a wave or a sine graph, then that would be the AC. Okay, so it's a DC for this case, and then state the energy conversion that takes place in this generator while it is in operation. So regardless whether it's a DC or an AC, a generator will always convert mechanical energy. Okay, so it's mechanical energy to electrical energy. So it's mechanical to electrical. And then can we give a reason why this generator is not suitable for transmission of electricity over long distances? So what we know about these generators is that there's going to be higher losses. Okay, there's going to be higher losses. That's number one. Number two, it requires a lot of current. Okay, it requires high currents for it to overcome the losses along the way and all of that. And then number three, we can also see that DC cannot be easily transformed. It's very hard to transform this DC current into an AC current. That's why it makes it a bit difficult. So just one of the reasons would be good enough, okay? Then they want us to calculate the frequency at which the coil rotates in the generator. The frequency at which the coil rotates in the generator. So we have 1, 2, 3, 4. Okay, did they tell us anything? Graph shows how induced current varies with time. So I'm going to have these two arms just to represent one full cycle. Okay, so if that is a full cycle, because it will be divided and then divided. So if that's a 0, that's probably 90, 180, and then blah, 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 360. So we know that the period is 0,02. If period is 0,02 from our formula page, we know that frequency is the reciprocal of the period. So frequency is going to be 1 over 0,02. Punching this into the calculator, 0,02, I'm getting 50. So that is 50 hertz. All right, then 9.5 is a definition, even if we skip that. Root means square. We have it in our books and stuff. So the equivalent current of the AC. So it's saying the equivalent DC current that will give us the same effect as the AC that will be flowing within the circuit. And then 9.6, they want us to calculate the RMS current that is delivered to the generator. So we know that the current is 1,2. So this is I max, okay? And then from our formula page, we know that I RMS, let's just refresh this page. Okay. We know that I RMS is gonna be I max divided by the square root of 2. So if this is 1,2 divided by square root of 2, let's just confirm that square root of 2. That is giving me 0,848, which is 0,85 amps. Okay, then 9.7, the graph below shows how the induced current varies with time after some changes were made to the operation. Okay, so now we can see that we're getting 1/2 cycle after 0,02. And then so on and so forth, which means the period is increasing, and we can also see that the induced current has decreased. Okay, so I can just, they're telling us to explain, fully describe the change that was made. So all I can say, since the current has reduced, we could look at the speed of the generator. That is 1. Chances are high, the speed was halved. Alternatively, we could look at the number of turns. Okay, the number of turns of the coil were reduced. Or even the area was halved. So all those could be reasons as to why all the changes that were made. All right, then question number 10. Source definition, suite 2 marks. Photoelectric effect. So we know that this is a phenomenon where electrons are ejected from a surface of a metal or a metal surface, or ejected from a surface when light of the required frequency shines upon it or is radiated on the surface. 10.2, they're telling us we have red light, blue light, as well as green light, as shown simultaneously on some potassium metal, as shown in the diagram. Each color of light consists of just a single frequency. We have two maximum kinetic energies of the ejected electrons, which are possible. We can have the 6,96 times 10 to the negative 20, and we can also have the 2,65 times 10 to the negative 20 joules. So each electron must have just one of them. Okay. There we go. Which color of light is responsible for ejecting electrons that have the maximum kinetic energy of 2,65? Now, if you're comparing the two energies, the 6, this is slightly bigger than this one. Okay. So if we are looking at E, which is HF, okay, we know that this energy is directly proportional to the frequency of the light. So if the energy is lower, which means we also expect the frequency to be slightly lower. Then from our light spectrum, okay, we know that Roy GPU. So if that is the case, we need to find out between the red, the blue, and the green, what does this arrangement represent? Is it frequency or wavelength? And then we take it from there. So we know that red has the longest wavelength. Okay. So if it is the longest wavelength, which means the frequency is the smallest, red has the smallest frequency compared to green and compared to blue. So if it has the smallest frequency, which means it will take on the smallest energy. So I'm going with red. All right, then 10.2.2, explain the answer in 10.2.1. So what we're saying is that red has the longest wavelength. The longest wavelength, or you can just technically tell us that it has the shortest or the smallest frequency. And we know that kinetic energy is directly proportional to frequency. So it has the longest wavelength, thus the small frequency, or lower frequency. Let's use lower. It looks physics-ish. Okay. That's lower frequency. And then we're saying energy is directly proportional to frequency. All right, then 10.2.3, they're telling us the electrons with a maximum of 2,65 are ejected by a light that is having this much of a frequency. Calculate the frequency of light that ejected electrons with the maximum of this much. So from our formula page, there's a formula of Emax that talks about the work function plus the EK. Let's confirm that. Which formula are we using? Okay, so we have it here. E is equal to W naught and then Emax. Okay, so this is what we're using. So what we can see is that between the two questions, the only thing that is shorting is the W naught, which is the work function. Okay, so I can start by looking for the work function. I'll say 2,65 times 10 to the negative 20. And then they told us the frequency is 5,85 times 10 to the 14 hertz. All right, so we need to get the work function. So what this is going to give me is that my HF is equal to the work function plus my EK max, which means my work function should be, I'll move that side, so I'll subtract. So 6,63 times 10 to the negative 34, that is Planck's constant, multiplied by the frequency, which is 5,85 times 10 to the 14. Now I'm subtracting the energy, which is 2,65 times 10 to the negative 20. So if that happens, which means my work function, 6,63 times 10 to the negative 34, okay? We are subtracting 2,65 times 10 to the negative 20. The other one was it positive or negative? We are multiplying somewhere with a 5. Okay. So times 5,85 times 10 to the 14. Okay, so I'm ending up with 3,614 times 10 to the negative 19 joules. So that is my W naught. Then I'll look at the other work function, sorry, the maximum kinetic energy is 6,96. Okay, 6,96 times 10 to the negative 20. So we need the frequency. So from that same formula, we can say HF is equal to W naught plus EK max. So our W naught is 3,614. 3,614 times 10 to the negative 19 plus the maximum kinetic energy times 10 to the negative 20. Okay. Is equal to the constant, which is 6,63 times 10 to the negative 34F. All right, then I'm going to divide both sides by the Planck's constant. That cancels that. When I punch that into the calculator, I'm ending up with 6,5 times 10 to the 14 hertz. All right. So guys, that is 10.2.3 for 5 months. Then 10.2.4, they're telling us that the intensity of red light is increased, while the intensities of blue light and the green light just remain the same. Okay. So what effect, okay, what effect will this change have on the rate at which electrons are ejected? What effect will this have on the electrons that are ejected? Okay, so what we can say is that when you increase the intensity, you're basically increasing the number of electrons that will be emitted from the metal surface. All right, then, so guys, that's that. I think the paper was just fair enough. Okay, so I wish you all the best in your preparations for paper 2. Please remember, this is just a suggested memorandum. This is not the actual memorandum. So yes, if you have different opinion about certain questions, feel free. We're not robots that we must get everything correct. All right, guys. Wish you all the best. Bye-bye. Hello, and welcome to this episode where we shall be looking at the proposed suggested memorandum for the Physical Sciences Paper 1 for November 2024 for grade 12. Okay, so we have 10 questions that we need to look at. We can use a calculator, instruments, show the formula, and all of that, okay? We're rounding off to 2 decimals. Okay, so with the question 1, which is the multiple choice, we have various options, okay, that we have for answers. And then we can just choose one to be our correct option. Okay, question number 1.1. They're telling us that several forces are acting on a moving object. Okay, so if forces are acting on a moving object, which of the following statements is correct when these forces are in equilibrium? So when forces are in equilibrium, it's more like Newton's first law of motion, that this body is meant to continue in its state of rest or its state of uniform motion. So in this case, it's moving. So the motion must be uniform unless it's acted upon by a net force. So the options we have, the velocity of the object is increasing. No, that is wrong. It cannot be increasing. And the object is moving at a constant velocity. There's some truth in that. The kinetic energy is decreasing. No. The object has a non-zero acceleration. I'll say that is also wrong because the velocity is constant, which means the acceleration must be 0. So option B would be my option for 1.1. Then 1.2, they're telling us that a stone is thrown vertically downwards from the top of the building and takes 2 seconds to strike the ground. If we consider the acceleration time graph below, okay, we're ignoring the effects of friction. What does the shaded area between 0 and t represent on the graph? So what we know, we can use the first equation of motion, where Vf is equal to Vi plus A delta t. Now, when you talk about this area under the graph, so this is the acceleration, and then this side is basically the change in time. Okay, so the area is, okay, the shape is a rectangle, which means the area is just gonna be A delta t. So from this, if we move the Vi that side, which means it's V final minus Vi is equal to A delta t. So this component here is what we call the change in velocity. Let's look at the options. Shaded area between that represents the final velocity, no? The change in the position, nope. The constant velocity of the stone is the change in velocity, which is option D. All right, then 1.3. If a ball that is moving horizontally has a constant momentum, okay, and then the kinetic energy is K, the ball collides with a wall and then bounces back horizontally. So immediately after the collision, the ball has half of the momentum, okay? Then the mass of the ball remains constant. Which of the following will represent the kinetic energy of the ball immediately after? Now, one thing we know about momentum is that it is directly proportional to the velocity, okay? The mass stays the same before and after the collision. So where there is V, I can represent it as a P, okay? Then if I'm looking at the kinetic energy, the EK for the first one is just a K. So which means my EK initially is going to be a half M, I'll say P squared, just in that sort of notion, because P is directly proportional to that. Now, if the momentum is now a half, which means where there is P, I'll represent it with a half P. Everything is squared. So squaring that, I'll get a quarter, then multiplied by a half MP squared, because this is a quarter p squared. Take this a quarter away, and then we have our original, which is k. So which means we're going to have a quarter of k. That is option A. Then 1.4. With 1.4, a force F is acting on a box. It moves from rest down a rough incline at a constant acceleration. The force is part of the incline as shown in the diagram below. A force F acts on a box as the box moves from rest down an incline at a constant. So if the box is moving from this point going upwards, we know that the FG parallel will be acting downwards, and then the frictional force will also be acting downwards. That is to the interpretation of the, I don't know, that's what I'm interpreting, okay? If the box moves from rest down a rough incline. Okay, so choose the option that correctly completes the statement. So the work done by the gravitational force is dash dash, the work done by the frictional force, and the work done by F. So if we know that F applied is greater since the object is moving upwards, which means to be a combination of these two, the work done by the gravitational as well as the frictional force. It should be summed up if we look at the F net being equal to MA. Okay, so we're going to say the work done by the but now the question is focusing more on the gravitational force, which means work done on the gravitational force must be the difference. Okay, so that is force applied is equal to the work done by the frictional force plus the work done by the FG parallel. So work done by the gravitational should be the difference between force applied and that. Okay, but if it is the difference, is it going to be greater or it's going to be less? It's going to be definitely less, but let's go with option D, that is focusing on the difference between the work done by the friction and the work done by F. So I'll go with option D. That is according to me. We can have various opinions about that. 1.5. If a ball is falling vertically downwards from point A, strikes the ground with a velocity v, okay, and bounces off, reaching a maximum height at p, as shown in the diagram below. Which one of the following combinations is correct for the direction of the impulse of the ball upon striking, and then the magnitude of the velocity with which the ball leaves the ground? Okay, one thing we need to know is that since this ball is striking the ground, okay, the direction of the impulse needs to be upwards. Because remember I said impulse is the same as the change in momentum. Okay. So if it is upwards, then we're looking at option A and option C. But then the velocity with which the ball leaves the ground. Now, since the ball is going to be in contact with the ground, there has to be loss of energy. Okay. And if energy is lost, remember the collision is not perfectly, or it's not perfect.